Welcome back to Physical Science 101. This is our final lesson of Unit 6. The subject of Unit 6 is light, and the specific topic that we're going to talk about today is optics, or how we can control light using lenses. Lenses essentially come in two types. We call one a converging lens and the other a diverging lens. And the distinction between these two is that a converging lens is thicker in the middle and thinner at the edges, and a diverging lens is thinner in the middle and thicker at the edges. In this diagram, we have a converging lens on top and a diverging lens on the bottom. So once again, you can see that the converging lens is thicker in the middle and thinner at the edges, and the diverging lens is thinner in the middle and thicker at the edges. Okay, so what does this do? Let's take a look at the converging lens. As these parallel rays of light come towards this lens, they are all bent towards the middle. That's because the top of the lens acts as a prism that bends the light down, that bends the light towards the thicker part, which is the middle of the lens, and the bottom part of the lens acts as an upside down prism that bends the light up. So the top of the lens bends the light down, the bottom of the lens bends the light up. In both cases, the top and the bottom are bending the light towards the thicker part of the lens. So the light bends towards the thicker part of the lens. So when these parallel rays of light come through the lens, they all converge on a point. And so you see that light coming together at a point. So what we say is that this converging lens has positive converging power. So this lens has a positive power to converge light on a point. So that is how we measure the lens. We measure the lens with optical power. And optical power gets a symbol of a capital P, and a converging lens has positive optical power because it converges the light to a point. Now the unit of optical power is the diopter, D-I-O-P-T-E-R, and it is symbolized with a capital letter D. Now for reasons that we'll see soon, a diopter is equal to 1 over a meter. So 1 diopter is 1 over a meter. Now, any of you who have gone to the optometrist and gotten a prescription, your prescription is in units of diopters. Even if that's not written on your prescription, those are the units that the optometrist uses for your prescription. So if you have a prescription with a positive number, if you have a positive prescription, that actually means that you are farsighted and your glasses will be thicker in the middle and thinner at the edges, also known as reading glasses. And we'll get more into detail on that later. A diverging lens is just the opposite. Okay, if we have parallel rays of light going through the diverging lens, once again the light is bent towards the thicker part of the lens, which in this case means that the light is bent away and does not converge. So a diverging lens diverges the light. Light on the top of the lens is bent up, light on the bottom of the lens is bent down. So a diverging lens has negative converging power. It does not converge light, it unconverges light, so it has a negative power. Now, if you are nearsighted, your prescription will have a negative value. You have a negative prescription. That means that your lenses will be thinner in the middle and thicker on the edges. Okay, now what can we do with this? Well, we can use lenses to form images of objects. Let me show you what I mean by that. Okay, what I have here is a flashlight, and on the front of the flashlight I've placed a slide, like from the old slide viewers, and the flashlight will shine its light through the slide so that the slide will become the object that we want to form an image of. Now, if I were to go very close to this screen and shine the light from the slide onto the screen, you can see, or you should be able to make out that there's something there. You should be able to see the astronaut in front of the Earth, maybe barely, not very well, not very well. But so the light is shining through the slide, and it kind of holds together so that there is something there to see. But as soon as I start to walk away, that very quickly blurs into really just a blue light. So there's nothing there that you can see. The image is still in that light, we just can't see it. It's not focused, it's blurry. But we can bring that image back out using a lens. I can take the lens and put it in front of the light so that all the light goes through the lens and then focuses in so that we can see the image again. Now notice that the image is upside down. That is a feature of images through a single lens, is that the image, notice that the astronaut's upside down, so the image is upside down. So now notice that if I move the flashlight closer or further, the image gets blurry. So what we've done by holding the lens a particular distance away from the screen is that we fixed the image distance. The image distance is the distance from the lens to the screen. So to have a focused image, I have to have the correct object distance. Okay? So when I move the flashlight back and forth, I'm adjusting the object distance. And there is one object distance that will give us a good image for a given image distance. Now if I were to change the image distance by moving the lens further away from the screen, notice that it gets blurry again. So for this image distance, I have to find the correct object distance. So as I change the image distance, I have to change the object distance as well to keep this in focus. If I were to step away again, it would get blurry again, and I would have to change the object distance again. So once again, moving in, I'm changing the image distance without changing the object distance. Now the object distance is not right. I have to find the correct object distance again. Okay, that was an image of a static object. Now I'm going to show you an image of a moving object. I'm actually here on the second floor of the University Center. I'm looking out over University Avenue, and there's cars passing back and forth. And I'm going to make an image of what I see outside of the window. So I have my lens, and I have a screen here. And by holding the lens just right, I can focus in, and you can see outside. You can see what I see outside. There's some cars passing by on University. Once again, you can see that the image is upside down. Here's the trees, here's the road, and here's the ground. You see some more parked cars, but now you can see all of these cars passing by on University Avenue. Okay, so as we saw, the distance at which an image is formed from a lens depends on two things: the power of the lens itself and the distance that the object is from the lens. If we put this into an equation, the equation is that the image distance is equal to 1 divided by the power of the lens minus 1 over the object distance. Or in our shorthand, d sub I for image distance equals 1 divided by, in parentheses, the power minus 1 over dO for the object distance. So the image distance equals 1 divided by the power minus 1 over the object distance. Now actually, if we knew the image distance and wanted to know the object distance, we can use this same equation, just swapping dO and dI. Let's put this equation to work. A lens has a power of 12.5 diopters, and we have two questions. What is the image distance for an object placed 0.16 meters from the lens, and what is the image distance for an object placed 20 centimeters from the lens? Let's work out the first one first, so please pause and work on that, and when you're ready, hit play, and I will work through it with you. Okay, let's draw our diagram. Here I have my lens. The power of my lens is 12.5 diopters, and that is also 12.5 inverse meters. A diopter is an inverse meter, and that's going to be important in our calculations. Here's our object, and the object distance is 0.16 meters. Our image is over here, and the image distance is what we want to know. Okay, we're going to use our formula. Image distance is 1 over power minus 1 over object distance. Okay, image distance is 1 over 12.5 inverse meters minus 1 over 0.16 meters. I'm going to put parentheses around there just to remind you to put them in your calculation. And so that tells us that our image distance is 1 divided by 12.5 minus 1 over 0.16, and it gives us an answer of 0.16. But what are our units? Well, we have inverse meters here. We have 1 over a meter here. We have 1 over a meter here. So we have a fraction in the denominator. To bring it to the numerator, we flip it over, and our 1 over meters becomes a meter, and our 1 over meters becomes a meter. So both of these, when we flip them over, become meters. So our units must be meters. So the image distance is 0.16 meters. So that's why it's important that a diopter is an inverse meter, and it's also why it's important that our object distance be in meters. And the next question, the object distance is going to be given in centimeters, but we're going to have to convert that to meters before doing our calculations. Otherwise, we will confuse our units. Okay, now for the second question. We have the same diagram. There's our lens with a power of 12.5 diopters. We have our object with an object distance now of 20 centimeters and an image distance that we don't know, that we want to know. Okay, we have the same equation where we have our image distance is 1 over power minus 1 over the object distance. So we have the image distance is 1 over 12.5 diopters, which is, in a diopter is 1 over a meter. So now, when we do 1 over the object distance, we have to put that in meters as well. Okay, so if the object distance is 20 centimeters, we want that in meters. So we have meters and centimeters, and 1 meter is 100 centimeters. That cancels off my centimeters. 20 divided by 100 is 0.2 meters. So we have to put our object distance also in meters, 0.2 meters. So now we have meters and meters instead of having meters and centimeters, which would confuse our units. So we have to make sure we don't confuse our units. Diopters is an inverse meter, so we have meters. So our distance also has to be in meters. Okay. So once again, we have 1 over meters, 1 over meters. We bring that to the top. That'll become meters. And what is our distance in this case? 1 divided by, parentheses, 12.5 minus 1 divided by 0.2. And so this would now be 0.133 meters. Okay, so we moved the object from 0.16 meters to 0.2 meters. When we moved the object, we changed the image distance. Okay, let's take a look at a special case in our equation. We have that the image distance is equal to 1 over p minus the object distance. Now, if the object distance is very large, then 1 over the object distance becomes very small, and then essentially it is completely negligible compared to the power. So for very large object distances, the image distance becomes simply 1 over the power. So what that says is that 1 over the power is what we call the focal length of the lens. So for objects at very large distances, they will all be focused at the same distance from the lens, and that distance that they're focused from the lens is 1 over the power. So 1 over the power is the focal length of the lens. That means that for higher power, the lens will focus very close to the lens, and at lower power, the lens will focus at a greater distance from the lens. Finally, let's talk about our eyes. The eye functions by forming an image on the retina of the eye. The retina of the eye is the back of the eye, which is the screen on which your brain sees things. So the way your eye works is that the lens of your eye focuses the light from an object onto an image on the retina. Now what that means is that since the size of your eye is fixed, the image distance is always fixed, regardless of what the object distance is. So when the object distance changes, so when an object moves nearer or closer to your eye, what that means is that the power of the lens of your eye has to change. And this is called accommodation. So the ability of a lens to change its power is accommodation. And in our eyes, the way it works is that our eye can actually be stretched. So when it's relaxed, it's kind of a thick lens, which means it has high power. But then there are muscles that will stretch it out and make a thinner lens out of it, which means that it has less focusing power. So your eye, the power of the lens of your eye actually changes to accommodate changes in object distances. And it keeps that image distance equal to the diameter of your eye so that the image is always focused on your retina. At least that's how it's supposed to work. Sometimes we have limited accommodation. For example, as we get older, we tend to become nearsighted, which means that our eye can accommodate for distant objects. Also, sometimes we become farsighted, which means that our eye can't accommodate for nearby objects. Let me demonstrate this for you. Okay, what you see here is you see an eye. The lens of the eye is right here. The retina is back here. And this eye is looking at a traffic light. We have a red light, a yellow light, and a green light. And as the eye is looking at this traffic light right now, that traffic light is blurry. The light from the red light is overlapping, the light from the yellow light is overlapping the light from the green light. So that traffic light is currently not in focus. So to focus it, the eye has to accommodate, or the focal length of the lens has to change. So I'm going to make the lens skinnier. So the muscles are going to pull on that lens and make it skinnier. And when we do that, you can see that now the image is pretty well focused on the retina. The red light is distinct from the yellow light, is distinct from the green light. So that light is now in focus. The person can see that light very sharply. Each of those lights is a sharp point of light. Now, if we were to get closer, there we go. If we were to get closer, we were to bring the light closer to the eye, notice that it's getting blurry again, okay, because we've changed the object distance, but we haven't changed the image distance. The image distance is fixed. The diameter of the eye is fixed, so the image distance can't change. So if we change the object distance, we have to change the focal length. We have to actually make a stronger lens. We have to let that relax and give ourselves a thicker lens that is stronger. And now that light is focused right on the retina. Okay, so you can see that the light is now focused right on the retina. The red, the yellow, and the green are distinct. So as the object distance changes, the image distance cannot change, so the power of the lens of your eye has to change. So that is what we call accommodation. That is the focal length of your eye, the power, the optical power of your eye changing as objects get nearer or farther to keep the image in focus, to keep the different parts of what you're looking at distinct on the retina, so you can see the difference between, say, the red light, the yellow light, and the green light. Okay, so that was a healthy eye. Now sometimes your eye is unable to accommodate and keep that image focused on your retina. We can correct that by using corrective lenses, and what happens in this case is that the power of the lens of your eye and the power of the corrective lens add together to give you greater focusing power if the corrective lens has positive power, or to give your eye and the lens less power if the corrective lens has negative power. Let me demonstrate that for you. Okay, so we're back here with the eye, and this eye is focusing on these three lights perfectly well when they're close up, but what happens if we move them back, and we're going to say that this eye is nearsighted, means that it can focus on things close up, but when things get further away, the eye cannot accommodate. So this eye does not have accommodation. This lens cannot accommodate enough to focus on distant objects. So this is a nearsighted eye. It can focus up close but not far away. Notice what's happening. The light is focusing before it gets to the retina. So the power of this lens is too much. So this lens actually has too much power. To correct that, we want to add some negative power. And for a negative power, we have to have a diverging lens. So this person would get a prescription with a negative power, and that will allow the light to relax. That will allow that will make the net power of this lens, of the eye lens and the corrective lens be exactly what it takes for the person to be able to focus on this light at a distance. So without the corrective lens, the light focuses in front of the retina, and the traffic light is blurry. With the corrective lens, the light focuses perfectly on the retina. So this is the perfect amount of power to focus on the lens, the eye, to focus the light on the retina. Without the corrective lens, the person's eye has too much power. Okay, so that would be a nearsighted person with a negative power corrective lens. Let's do a farsighted person, meaning a farsighted person can actually focus on that light when it's far away. So this is a farsighted person. That person can focus that light just perfectly when the traffic light is distant. Notice that they're green, yellow, and red are all distinct. But now this farsighted person is not going to be able to focus when the traffic light gets close. So the traffic light is close. If the person's eye cannot accommodate, then what the person sees is blurry. Notice the green is starting to overlap with the yellow, is starting overlapping with the red, and each of them is larger. So instead of a small point of light, the person is seeing big balls of light. So that person cannot focus up close. Once again, notice what's happening. The light is not focusing by the time it reaches the retina. So that means that the power of this lens is not enough. We need more power. How do we get more power? Well, we bring in a lens with positive power. So that would be a reading glasses that have positive power. And with this reading glass, adding the power of the person's own eye lens to the power of the corrective lens, now this person can focus, can distinguish the green light, the yellow light, and the red light. So this is correcting for farsightedness. Someone who cannot focus up close needs more power. So that means that that person needs a positive power corrective lens. Okay, so that is why if you are farsighted, you have lenses with a positive focal power, and if you are nearsighted, you have lenses with a negative focal power. Our final question is, the condition of farsightedness, or hyperopia, can be corrected with or an A, diverging lens, B, converging lens, C, flat lens, or D, combination of diverging and converging lenses. Okay, pause please, think about it, and when you're ready, hit play again. Okay, as you can see from the diagram, and as we just discussed, farsightedness is corrected by adding power. So to correct farsightedness, you would have a positive power lens, which is a converging lens. So the correct answer is B, converging lens. Okay, so that is the end of Unit 6, Light. In the next lesson, we're going to start Unit 7, which is our final unit, and it's going to be on the subject of nuclear physics, which is essentially telling us where everything that we're made of comes from. Until then, think science.